We're going to start by talking here about numerical transients. So for a transient, we have to include the effect of time. So now things are changing with time. So we start with this form of the heat equation. Basically what we've done here is we've taken rho c dt d time equals k d squared t dx squared plus q dot over k. We've assumed that there's no heat generation, and we divided through by the thermal conductivity to get 1 over alpha on the time derivative side. So this is just derived right from the heat equation. Now, the next thing we do is address the time. So here we have Tmn, which is our grid points, but we also have the superscript p. Here, p indicates the current time step, so the present, and p plus 1 indicates the future time step, so one time step in the future. Then we have to look at central differencing. So we use what's called central differencing for the second order derivative. And central differencing just is this definition. So if we have our x, we have m plus 1, m minus 1, and mn. We can also define d squared t dy squared, but for the time being we're just going to look at 1D problems where we just have x. So we have a problem here. At which time do we evaluate d squared t dx squared? Do we use the present time with superscript p, or do we use the future time with superscript p plus 1? Now it turns out we can use either, but each choice has some particular benefits and drawbacks. If we use time p, which is the present time, we call this the explicit method. So what's convenient here is we can calculate the temperature at the future time only using information we know now. So we can solve this equation for t at p plus 1 on the left side, everything else on the right side. What's convenient here is we can march through time. We don't have to actually iterate the solutions at each time step. It's important to note that the accuracy does depend on the time step. Smaller time steps are going to be more accurate. But we also have another restriction on our time step, and it's stability. So what can happen is, because you're using the values at the current time step, you can actually overshoot the value at the next time step, and this is going to cause numerical oscillations. Your solution is going to go jump back and forth around a value. So we have to be careful to make sure that we don't have this problem, and the way we do that is we make sure that this 1 minus 2 times Fourier number must be greater than 0. So for a 1D problem, that means the Fourier number has to be greater than or less than 1/2. So the Fourier number, which is alpha delta t over delta x squared, has to be less than 1/2. So this gives you a maximum delta t. Delta t must be less than some value. So for explicit problems, you may have very, very small time steps required, and then you have to do many, many, many time steps, and it can take a long time. We can adjust that for this sort of implicit approach. So in the implicit method, we evaluate the spatial derivatives at the new time step, at p plus 1. So now we can no longer evaluate it just using the previous time step. We have to use the values at the new time step, which we don't know yet. So this requires we have an iterative solution at every time step. So in CFD, you'll often see inner iterations. So what we say is a time step is an outer iteration, and then when you have to iterate the solution in each time step, those are inner iterations. The benefit to this method is that the solution is always stable. You can see we don't have any 1 minus Fourier number terms in this equation. So we can use a larger time step and avoid the oscillations that occur with the explicit method. So we can actually save on computational time. Even though we have to iterate at each time step, we can have much larger time steps. Now this does reduce accuracy. So the accuracy of your solution is still better when you have smaller time steps. However, you can significantly reduce your computational time and get a solution much more quickly. So it's more efficient. We can also use the Crank-Nicolson method. Now the Crank-Nicolson method basically takes the implicit method and the explicit method and calculates a weighted average of the two. So it has the weaknesses of both. It's unstable for large time steps, and it requires iteration at each time step. So the question is, why would you want to use this method? And the reason is because we're trying to reduce error. The explicit method typically overestimates the change in temperature at each time step, while the implicit method typically underestimates the change for each time step. So by using the Crank-Nicholson method, which is also sometimes called the semi-implicit method because it's partially implicit, allows us to reduce the error and get a closer estimation of the actual time step. So the reason you would use this is if you need very, very high accuracy for a particular problem. A common value for this f in this equation, which is our weighting factor, is 0.5. And then it's just half the implicit equation and half the explicit equation.